Hello, everyone. Hope you're doing well. We're going to continue talking a bit about what special types of normed vector spaces there are out there. We'll start with a couple of applications of things we've been talking about a little bit already when it comes to normed vector spaces. One of the things that I want to discuss are in that this video lecture has a few optional things, a couple optional tags with it. One of the optional videos comes from an application of something we've already talked about, finding that you could write something, an orthonormal set with the continuous functions from negative pi to pi with 1 over square root of 2, together with the function sine of nx and cosine of nx. And we know that to be kind of the basis for Fourier series and how they interact. But there's a neat little interaction here with Fourier series and Stone-Weierstrass. And there's a neat intersection between these two areas that comes from figuring out whether this set becomes an orthonormal basis. We'll talk a little bit about basis first, just to kind of get a general understanding of that, and then we'll go into this as a bit of an application so that we can see kind of what bases do and how they interact with this. We'll also touch a little bit on something that we talk about in Math 632 or 689, depending on your year, which is looking at the principal axes theorem. We're going to revisit this for just a second here in another optional part as a way of introducing what we're going to be talking about next, which is the space of linear operators. Namely, using this principal axes theorem, we will be discussing the proof behind how we know to calculate the operator norm of a matrix to be the square root of the lambda max, the largest possible eigenvalue of the matrix A transpose A. So we'll go through a little bit of that and do a bit of proof in that, and then we'll move into linear operators. So those are our two main ideas, each one with a little bit of an optional component so that we can either give an application or motivate something. Of course, if you're just here for the mathematics of it, which is always an exciting thing to do, you can make sure to be looking at those at a later time. We won't be testing over things like that. So just letting you know that those things exist out there in the world and giving you a little bit more information, some neat things to kind of go along in there. So let's talk a little bit about these two concepts. First, we've talked about this in normed vector spaces, that you can have two different types of bases. Let's recall what those were real quick. If you have an infinite dimensional vector space, like the space of polynomials, then you can decide whether or not that is a Hamel basis or a Schauder basis, depending on the space that you're looking at. Every vector space has a Hamel basis, but some have an actual special version of a basis called a Schauder basis. And we'll talk a little bit about Schauder bases in what is to come. And we'll talk about this with regards to some of the bases. The theorem that I'll use for bases here is going to be a little bit different than the one that is used in the textbook. I think the textbook likes to use a lot of different propositions to discuss bases, and I wanted it condensed down into one little box of summary that we can take a look at. But first, let's remind ourselves about the difference between Hamel bases and Schauder bases. A Hamel basis is something that says that, first, that the span of the vectors that you get is going to be equal to the entire space. That is, that everything inside of the space can be written as the sum as I goes from 1 to n of alpha sub I, b sub I. That this is equal to the entire space whenever alpha sub I is a number inside of our field, whatever that might be, and n is just some natural number, that this is equal to the entire vector space V, so the entire space. The Schauder basis is a little bit different. Schauder basis allows you to throw in some notion of infinite bases. So you're taking convergence of these vectors in norm as you take them along. So this can be an infinite sum that converges in the norm of your space. What I mean by convergence in norm is that this vector, if I call this vector x, then the norm of the partial sums of this series, thinking of this as like the norm inside of a norm space, then the difference in norm between x and the partial sums of this series goes to 0 as n goes toward infinity. So when I'm writing something like that, that's the sort of thing that I mean, is that you can be taking partial sums of this and then continuing to see those grow. One thing that has to happen there is that the values of these alpha sub I should either be going down or the norms of the b sub I should be going down as you do this. In the case of an orthonormal basis, your values of the alpha sub I are definitely going to be decreasing as you go through this. The way I know this is that we had this theorem that talked about how the tail end of a sequence has to decrease in norm as you continue to let n go toward infinity. So either the alphas of I have to go down or the v sub I do as that happens. So you can imagine this as something like a power series, perhaps, of a given sequence of functions. We kind of given an example here with something like, which was the one that we used? I think we used the one for e to the x, which is the sum as n goes from 0 to infinity of x to the n over n factorial, and talked about how this can give us a different element that's not in the space of polynomials, but would be in the space of power series. So this is an example of a Schauder basis where you're allowed to use infinite sums inside of this, wherever here alpha is inside of your field. And here you can make the sums whatever you would like them to be. So you let these alpha sub I, b, and k, and then you ask for a specific thing to happen. Either the alpha sub i's or the v sub i's go in norm towards 0. We'll go ahead and in this case, we'll start looking at orthonormal bases and start looking at what these Hamel and Schauder bases look like in this case. Well, if we're looking at a Hamel basis, not much is going to change by knowing the lengths of these vectors are each going to be 1. Because the length, whatever this is in norm, it's going to be bounded above by some finite value just by using the triangle inequality on a finite sum. But an infinite sum makes that a little bit tricky. Let's say, for example, we're looking at the space of little L1. In the space of little L1, you are considering the set of all sequences, this is x sub n in the sequences of real numbers, such that the sum of the absolute values of the x sub n is going to be less than infinity. N goes from 1 to infinity. So there we are. The basis for this space is you can just take the kind of what we have been using as a standard basis for these spaces of sequences, which is you take the sequence that is 1 in one spot and 0 in all of the other spots. So for example, this would be a basis for this space. It's in fact a Schauder basis. But that doesn't mean all possible linear combinations and infinite linear combinations, we might call them, all possible infinite linear combinations of these vectors live inside of the space little L1. For example, if I just tried to add all of these sequences together, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. If I tried to add all of these together, I would get the sequence 1, 1, 1, 1, so on and so forth. But this is not a sequence inside of the space of little L1. Even though this is still a Schauder basis for this, there's a constraint on this space. And that constraint is that the scalars that you use in this orthonormal basis have to go towards 0. We'll talk a little bit about that here in this upcoming theorem. This upcoming theorem, I'll be marking this out as I don't think that it's, I think the name is a little bit of a misnomer. It is used as a name for this property, but I don't like calling it completeness because I want us to talk about completeness in terms of Cauchy sequences converging and not make it confusing in that other spot. So let's talk a little bit about what a orthonormal basis might look like. In a Hilbert space, there's a lot of different ways for us to define something to be a orthonormal basis. So let's talk a little bit about that. First, I mentioned the term Hilbert space. Hilbert space is an inner product space where Cauchy sequences converge. We can use, since this is a norm space, we can use the same property that we had from week 8. Remember that we said that an inner product space was, or a norm vector space was complete if absolutely convergent sequences converged. Absolutely convergent series converge. So that's what we're meaning by completeness here. It's that same sort of notion as to there. If you are in a complete space, then the following conditions are equivalent. Here's a few that we saw a little bit in our reading. The second one here is Parseval's identity. This is one that says that if you have something like Besel's inequality, then this less than or equal to can become, or rather a greater than or equal to here, can become an equals to if your sum over here is as big as it can possibly be. The idea here is this: if you have, for each of these E sub alphas, or E sub n's I should be calling them, need to go back and change these labels here, and in the natural numbers, and in the natural numbers, just so that I have my labels being consistent. Then these E sub n, if I have the largest possible orthonormal sequence inside of a Hilbert space, then I might call that a basis, a place in which the entire length of the vector is accounted for by each of its projections. Let me give an example of this. The norm of the vector 1, 2, 3 inside of R3 is given by 1 squared plus 2 squared plus 3 squared, and then square rooting it. If I went through and took that length and squared it, then this is exactly the formula that I would get. You might notice this as like taking each of the components and squaring them and adding them together, just like we do in the definition of length, but you can also see it from another way. You're taking the projections of the vector 1, 2, 3 against each of the x, y, and z projections that it has onto the x, y, and z axes. For example, the projection of 1, 2, 3 onto the x-axis would be 1, 0, 0. The projection of 1, 2, 3 onto the y-axis would be 0, 2, 0. And the projection of 1, 2, 3 on the z-axis would be 0, 0, 3. We could see this as just taking the lengths of each of these vectors, squaring them, and then adding them up together, taking the x, y, and z projections on that space. Now I'm going to get rid of this purple here a little bit just to be able to kind of help us see clearly what's going on in this condition. But this is exactly the equality that we're using in using Parseval's identity. To find the length of a vector squared, you just take each of its components, square them, add them together. And if you want the length squared, you don't have to take a square root. If instead I looked at the projections of the vector 1, 2, 3 onto each of its basis elements, took those lengths, squared them, and add them together, then that's exactly what I get as well. I get the exact same thing. The difference here is that the vectors that I was choosing to project on, E1 being 1, 0, 0, E2 being 0, 1, 0, and E3 being 0, 0, 1, that each of these vectors, when taken together, form a basis for the space of R3. If I had only taken a couple of them, like if I had ignored this one right over here, what I would get is a sum that's not exactly complete. I would not have a basis for R3. I would just have an orthonormal set in R3. And taking the projections of 1, 2, 3 against this orthonormal set only gives me 1 squared plus 2 squared. It gives me a sum of squares of lengths that is not quite equal to the entire sum here. That's how we actually get to see kind of Bessel's inequality in action here. Bessel's inequality says that the length of this vector squared is going to be greater than or equal to the sum of the squares of the scalar projections of these vectors onto the orthonormal set. If what you have is an orthonormal basis, then what's basically happening is that you're covering all of your corners. You're covering every single direction that your vector could be going in. You're adding in the z component. So when I take my vectors E1, E2, and E3 and work with them here, then this is for me the length of the vector x in a product with E1. This is the scalar projection of the vector x onto E1. And then this right here, this is the scalar projection of x onto E2. This right here is the scalar projection of x onto E3. And if I go through and look at each of those and add them all together, then this is exactly what I get here, taking those and squaring them, of course. That's the sum of everything equaling the norm. The difference there is that the set that I had to take my orthonormal projections for was itself a basis for the space. Not only an orthonormal set, but also a basis. That's what we mean for an orthonormal basis here. So we see here that any orthonormal set that satisfies Parseval's identity, that is, whenever you have a vector x inside of your space, that in fact the norm squared of that vector is the sum of its scalar projections squared onto the orthonormal set that you have, then we call that orthonormal set an orthonormal basis. But we could do this for each of these other conditions as well. Taking a look at condition 3 here, you can erase this so that it doesn't look as messy. The question, point 3 says that you can take a vector x to be equal to the sum of its scalar projections onto each of the individual vectors E sub n, where the sum on the right has only countably many non-zero terms and converges a norm regardless of rearrangement is a lot of words. But basically what that means is that the set E sub n is itself a Schauder basis for the Hilbert space. That's because you have that every vector x, for all x in this Hilbert space, X can be written as a linear combination, an infinite linear combination, if you will, of the inner products of X with these E sub n times this E sub n. These are the scalars. These are the vectors. This is a linear combination of the vectors E sub n. So that gives us a Schauder basis. It could be infinite. Only countably many of the non-zero terms can be non-zero, but that still means that you're looking at a Schauder basis, something like this. So one way to show that you have that an orthonormal sequence is a basis is that it satisfies Parseval's identity. Whenever you take a vector, you can always find its length by adding up its scalar projections against the elements of the orthonormal sequence you're working with. Condition 3 says that you get to show that it's a Schauder basis. Every vector can be written as a countable linear combination of the orthonormal sequence that you're working with. This last condition is the simplest to write and is also the most useful. I'll erase the kind of the stuff that I've been marking out here to say this. If the inner product of the vector x with every single element inside your orthonormal sequence is equal to 0, then the vector itself is equal to 0. Here's an example of that. So here's how we could see this. Let's take our favorite vector x equal to 1, 2, 3 once again. And let's say that we have an orthonormal sequence. Let's talk about it being like E1 equals 1, 0, 0. E2 is 0, 1, 0. And E3 being 0, 0, 1. Now notice I keep talking about this like it's an orthonormal sequence, but you might immediately say, John, this is not an infinite sequence of values. And you're absolutely right. This could be a finite sequence if it needed to be. And if I needed to do that, I would put in a little bit of an extra like finite in parentheses here. But I'll go ahead and just say that this is something that we can take expectation of. Think of it this way. If we were looking at a finite sequence, we'd be looking at a space like R3, something that has its own kind of version of it in something we might see in like a 300 level course, or maybe in just 632 or 689. So we have some theorems for that. These theorems supplement those for what this might look like in the infinite case, but they also do work in the finite case. So let's take a look here at this, what this would mean. Let's say that you have a vector x. And let's say that when you take its inner product against any of these three vectors, you always get 0. Well, could this be the vector x? The inner product of this vector with respect to each of its components here is equal to 0. But that's not true of the vector 0, 0, 0. Its inner product with respect to any of these three vectors would be equal to 0. Now, condition 1 is a little bit stronger than just saying that the inner product of the vector x with any of the vectors inside of this set is equal to 0. It wants to say something stronger. It says that the vector x equals the 0 vector is the only one that can have this property. If the inner product of that vector with any of the vectors inside of this orthonormal sequence is equal to 0 for all possible elements, then the vector x is the 0 vector. For example, let's say that I had the vector 0, 0, 2, and I checked its inner products with E1 and E2. Its inner products with E1 and E2 are both 0. Inner product with x and E1, that's 0. Inner product with x and E2, that's also 0. So I might be forced to conclude that the vector x is equal to the 0 because its inner product is 0 with every single vector inside of the orthonormal sequence. But the issue is that without E3, this is not a basis for R3. Because it's not a basis, I actually have something that is a counterexample to this argument. The vector 0, 0, 2 is not the 0 vector, and yet its inner product with each of these other vectors is equal to 0. That gives me a counterexample to show that the set of vectors that I have is actually not a basis. So when I say that condition 1 is very useful, it's often very useful as a counterexample. It says that the set of vectors that you have are not a basis, because I can find a vector whose inner product is equal to 0 for all of the vectors you gave me, but it is not itself the 0 vector. In this slide, I just kind of go through and talk a little bit about what each of these conditions mean a little bit more, because I feel like it's important for us to really just kind of talk through this. And I think that what we've done with some of our examples is a pretty neat proof quote unquote, of what these things mean and how they are equivalent to each other in terms of the basis. In the 2 slides that are beneath this, I do give a formal proof. If you'd like to take a look at that, feel free to. I'm not going to go through it in this video. It's just there for you to talk about. So instead, what I'll do is I'll talk a little bit more about each of these conditions just very briefly. I've already talked a good bit about each of them, but let's do just a little bit more. Condition 3 was the one about how you could take an x and make it the sum of the inner products of the vector projections against each of the elements inside of our orthonormal sequence. So you could write any vector like this. This would be true for all x inside of our Hilbert space, whatever we call it. Then this is our typical notion of a Schauder basis, with the slight addition that we actually know the scalars that are given in our basis, which is the inner product of x and use of alpha. Note that 2 replaces the inequality in Besel's inequality with an equality. Looking back at that proof for Besel's inequality, we had a notion of something that we could get rid of. There was a reason that we could do like this is eventually greater than x minus. There was some sort of like, basically there was a way to get this inequality for the greater than or equal to the norm of x. And the slack variable, the thing that we were allowed to get rid of, was this norm of x minus p of x. If we actually have an equality there, then that slack variable is equal to exactly 0. Kind of going back to that proof for just a second here so that we can highlight that, since we did go through it quickly during our video. What we had here was you could take any vector and say this is going to be greater than or equal to. If this was actually an equal to, well, then take a look at these 2 terms. These are exactly the same. So the only thing that you can conclude is that the norm of the vector that you're looking at minus the projection of that vector onto your orthonormal sequence, that norm squared is equal to 0. Hence, the norm itself would have to be equal to 0 for that vector. If I'm writing x instead of u, then you have what I have right over here, which is that the norm of x minus p of x squared is equal to 0. That is, x has to be equal to p of x, because this has to be equal to the 0 vector. Because if this is a norm of something is equal to 0, then we know by the definition of norm that the vector itself is equal to 0. So this is true for all possible vectors if this is going well by Parseval's identity. So whatever we are projecting on, x is already in that space. So p is the identity projection, meaning the projection of any vector onto the space that we are projecting onto is exactly that vector. And if that's true for every vector inside of that space, that's saying that x is already in the set of vectors that we're projecting on. And that's true for all of them. So that means something about the space we're projecting on. It has to be every single vector. Well, how could we be projecting onto every single vector unless the vectors that we're projecting on form a basis for our space? We are projecting onto E1, E2, and E3 all at once, and that's the entire space. That's exactly what we have in that picture. Condition 1 is the most useful to us and essentially says that no non-zero vector is orthogonal to all vectors inside, all vectors that are in our orthonormal sequence. So since we are understanding this as a basis, if x were orthogonal to all E sub n and x was non-zero, then we could just add x to the set of all of these vectors E sub n and get an even bigger basis. But we know that bases should be essentially the same size, that bases are the largest possible linearly independent sets. So if x were orthogonal to all E sub alpha and were non-zero, you could just add it in there, since you just be adding in one more linearly independent vector that gets to go off in a different direction. So again, here is a little bit of that proof if you're interested in it, written in kind of the same notation as what we've been using. You might notice that the real component comes back in this one. So I wanted to mention that we had talked about that in the previous video lecture. That's something that we have right over there. But this is one of our optional parts. This is showing that this set is an orthonormal basis. Now, we are already using the fact that we know that this is an orthonormal set. But to show that something is a basis, we want to use some of the conditions that we've just been talking about. I'm going to use condition 1. So we already know that this is an orthonormal set. Want to show that if you have a function f, which is inside of the space that we typically work with, and I should have added this to the problem, that this is an orthonormal basis in the continuous functions from negative infinity to infinity, and negative pi to pi, that if you have a function f that is inside of this space of continuous functions such that the inner product of that function f with each of the elements inside of this orthonormal basis is equal to 0, then we would need to conclude that f is actually the 0 vector, that f is the 0 function. So this is what we want to show, and this is by condition 1 of our theorem. If we can show that the inner product of this function with any of the other functions inside of this set is equal to 0, then the function itself is equal to 0. We have essentially shown that this is a basis by our previous theorem. So let's talk a little bit about that. What does it mean to take the inner product in the continuous functions from negative pi to pi? That means that we're going to be taking the integral of f of x times 1 over square root of 2 dx, going from negative pi to pi. We could also take the integral of f of x times sine of n of x dx, as well as the integral of f of x times cosine of nx, each going from negative pi to pi. And we could get each of these to be 0. Now, I could have also written the 1 over pi out here, but I decided not to. I decided to just multiply everything by pi, just to make it look a little bit nicer. So if I'm starting with a function f that has this being true, then here's what I'm starting with, that the integral of f of x times any of these other functions is equal to 0. I would need to be able to claim that the function f itself is equal to 0. And you can imagine that's a pretty bit of a tricky ask, because for a function to be equal to 0, it's hard to be able to determine that by even saying, okay, the integral of the function is 0, because that can just mean that you have just as much area underneath the x-axis as you do above the x-axis. This function does not have to be a non-negative function. And then multiplying f of x times sine of nx and cosine of nx, that doesn't seem to really be helpful or useful to us in this sort of equation, at least not as written. We need some other sort of tool to help us get here. So let's do a little bit of setup just to kind of get us started. Let's do a little bit of setup. We kind of talked a little bit about our goal. Let's talk about how we're going to get there. The setup for this is going to look a little bit like this. Let's take a set S to be the set of all functions g that are continuous functions from negative pi to pi. And let's define the set S to be all of those functions that have the integral from negative pi to pi of f of x times g of x dx equal to 0. For example, S is a non-empty set, and it contains everything inside of this basis. You know what else it contains? It contains the span of the orthonormal sequence that we've been looking at, the span of 1 over square root of 2 cosine nx and sine nx. Because if I added 2 of these fractions together, then or any 2 of these functions together, that would still be 0 because I'm adding 0 to 0. I could also scalar multiply any of these functions, any of the functions given here in this orthonormal basis, and I would still get 0 from this integral. So S contains the span of this set. Here's what I want to claim. I want to claim that S is equal to the entire space of the continuous functions. I want to say that actually, no matter what function you choose for g of x, if you integrate it against f of x, you're going to get 0. So why would that help me? If this is true, then the function f itself is an S. So the integral from negative pi to pi of f of x times f of x, or f of x squared, is equal to 0. But now, because we're looking at real numbers for the values of this function f of x, this now has to be a non-negative function whose integral is equal to 0. There can be no area under the curve, so this has to mean that the function f is equal to 0. So that's going to be our claim, is that this set S, which is all of the functions in the continuous functions from negative pi to pi, that integrate against f to give 0, we're going to claim that that's the entire space. Now, that seems like a ludicrous claim. Again, it seems hard because you only have functions of these forms to start with. You also happen to have the span of all things inside of there, but that seems to still be a little bit tricky. But a span is one of the two things that you need in order to be able to form an algebra. Recall that an algebra of functions is something where I can take addition and scalar multiplication of any of the vectors inside of a given space, and I could still get something inside of that space. I also would need to show something else, which is that if I multiply any two elements inside of the span of a given space, then I still get something inside of the set. So I'm going to start using, so I want to use Stone-Weierstrass to show this. We first show that the span of this orthonormal sequence is an algebra. The way we can do this is we take a finite sum of any elements that have these functions as a part of them, and we multiply them together, and we see if what we get is still a linear combination of these functions. To be able to do that, we just have to figure out how to multiply something that's of the form cosine nx and something of the form sine nx, or cosine nx and cosine mx, and multiplying these guys together. So it's okay and sufficient to show that we could just multiply any elements here inside of the spanning set. But remember that we have some formulas that help out with exactly that. Cosine nx times sine nx, mx, for example, that this is equal to a sum of sines and cosines. Sine of n plus m times x, 1/2, plus, I believe it could have been minus, sine of n minus mx over 2. This is true by, once again, product to sum formulas that tell us that we can rewrite any product of cosine and sine as a linear combination of sine functions. Same thing with cosine and cosine. I can multiply two of those functions together and get that to be a product of sum formula. I could rewrite cosine times cosine as something of the form 1/2 cosine of n plus m minus x, or times x. And I believe that one might be minus 1/2 cosine of n minus m times x. So even if it's cosine nx and cosine of mx, whatever those n and m might be. And the same thing can be done with sine of nx and sine of mx. And we could just keep going through all of this, but product to sum basically gets us there. Product to sum says if I multiply any of these functions of these formed together, whether it be cosine and sine, cosine, cosine, or sine and sine, then what I end up getting is something that is still a linear combination of sines and cosines. Of course, if I multiply these things by 1 over square root of 2, I also don't have an issue. That's a scalar multiple of whatever the function is that I multiplied it by. So that is sufficient for me to say that this set is indeed an algebra. Not only is the spanning set an algebra, but the span itself is an algebra. So what we've shown so far is that we have an algebra. What we'd like to do now is say the other things that Stone-Weierstrass asks for us to show. Namely, we'd like to say that, go ahead and give me a little bit more space here. Gotta work through this. Give me a second. Now we want to show that that algebra has all of the other things that we would like. Well, I'll leave some of these details for us to take a look at as a team, and you can help lead us on that little project there, which is to show that this algebra is indeed that it separates points. And you can kind of take a little hint there is that sine of x, sine of 2x, sine of 3x, so on and so forth, that this is enough. In fact, actually, yeah, sine of x, sine of 2x, sine of 3x, these are enough to kind of show this. And if you don't get it with sine of x and these things, you can actually just throw in a cosine of x and you can get there. So sine of x and cosine of x are enough. And that it vanishes nowhere. And the hint there is that you have the function 1 over square root of 2, which would vanish nowhere for that space. That means that you have, therefore, that basically that this this set, the span of these elements of 1 over square root of 2 cosine nx and sine nx, is dense in the continuous functions by Stone-Weierstrass. This will imply that because S contains this, that S is dense in the continuous functions from negative pi to pi, where S was that set that we defined to be all of those functions which integrate against the function f to give me 0. Well, S is dense. How do I get that S is equal? Well, I just need to show that S is closed. S is closed would imply that if g sub n converges uniformly to a function g, and the integral from negative pi to pi of f times g sub n is equal to 0 for all n, then the integral of f times g, negative pi to pi, is equal to 0. That's what it would mean for this to be closed, g sub n being a sequence of elements inside of S that limit to get me to the function g. And this is definitely true. We can check that out ourselves. Notice that's the integral of f times g, negative pi to pi, is equal to the integral of f times g minus g sub n plus the integral of f times g sub n. So basically, how am I getting this? I'm adding and subtracting f g sub n to both sides. This is something that I think that I could get to be small because, in fact, it's equal to 0 for each of these terms. So this is equal to 0 by our construction. And g minus g sub n, we have this convergence going on here, which means that g minus g sub n is going to eventually be less than or equal to 2, or is going to be less than epsilon eventually by our definition there. So this can be 2 pi epsilon times the integral from negative pi to pi of the function f dx. So this is less than or equal to here. And because this is a bounded integral, because f is continuous and it has an absolute max and an absolute min on its interval from negative pi to pi. Because this is a bounded function, this is a finite value, and because of that, we can just let epsilon go to 0. And now we have shown that S is equal to the space of continuous functions, which shows that the function f of x is equal to 0, and this completes our claim that this was indeed an orthonormal basis. So it's a neat little puzzle to see that Stone-Weierstrass actually gets us there. So this is kind of the little pieces that we used. We started by doing a little bit of goal reaching. So here's our goal. We did a little bit of setup to kind of get us started, and then we did an application of Stone-Weierstrass. And then after we finished up, we did a little bit of epsilon argument, and that got us through this entire argument. This is a neat way that you start seeing all of the theorems that we've been talking about so far interweave with each other as we keep going through in mathematics. You might think Stone-Weierstrass, I only use it in very particular arguments, and you don't. You see these theorems just pop up in random places as being something that's useful in ways that you never expect. You just kind of stumble into it a little bit and suddenly, wow, okay, I didn't expect that. But here, I'm glad that I've seen it before because I looked at this and realized that now I get this as an orthonormal basis, and I can start doing some Fourier analysis with these functions. So this is a neat little application of the theorem we just learned about together with Stone-Weierstrass, and that'll complete what we're talking about right now with bases. Just a neat way of synthesizing the things that we have done here so far. So far, what we've talked about is that all of these inner product spaces, if you have an orthonormal set inside of them, there's a nice way to get a basis for those spaces. But let's go ahead and move on to something else that we've talked about a bit with norm vector spaces, and that is matrices. Matrices are an example of normed vector spaces that have norms on them based off of what we've been calling the operator norm. The operator norm we defined to be this. If you have a matrix A, which say it's an m by n matrix, so that is a matrix A, then you would have that A itself maps a vector in Rn to the vector in Rm. Then the way that we define the operator norm on the matrix A is that we look for the supremum for all x, vectors x inside of Rn, such that the norm of x in Rn is equal to 1 of all of the possible values of the norm of A sub x. this being an element in R sub n, R to the n. This norm of A, what it is essentially saying how far could you possibly stretch vectors from your domain space to get them somewhere in the range space. And we've given a way of talking about how you can calculate the operator norm of a matrix using this value of the value of lambda max. Got a little extra absolute value here. This lambda sub max is the maximum value of all the absolute values of all eigenvalues of A transpose A. So that is the notion of an operator norm. Up here, you can see some of the definitions that we worked with in the past. Perhaps you've seen positive semi-definite in the past. So you've also seen us talk about the dot product. So that's a little bit of an abbreviation of some of the things that you've likely heard us talk a little bit about before. But one thing that is neat about pulling in A transpose A into this format is that A transpose A is guaranteed to have eigenvalues. There are eigenvalues, or there are matrices, even in the 2x2 world, like this rotation matrix by 90 degrees, that have no eigenvalues. So we cannot define the operator norm of a matrix by just looking at its own eigenvalues. It might have none. However, a symmetric matrix like A transpose A, one whose transpose is itself, has a basis of eigenvectors. It has enough eigenvectors to get you wherever you would like to be. And one of the things that we get to learn from that is that we can now find the largest possible eigenvalue amongst those and use that as a definition here for this correlate for how much we're stretching or shrinking space. But let's talk a little bit about why that ends up being the correct notion here. And we can talk about that after we've briefly reviewed what the principal axes theorem is. The principal axes theorem says that if you have something of the quadratic form, this quadratic form is something in which you plug in a vector x and you take a symmetric matrix like this, and you take x transpose times A times the vector x. If you have an arbitrary quadratic form, then there is a real orthogonal matrix S, such that you can take this Qx to be a sum of squares of the vectors of the elements of the vector x tilde, which is S transpose times the vector x, with some certain amount of eigenvalues. We'll talk a little bit about how that's useful in the proof later on, but the main thing to be taking in here is that whenever you have a collection of eigenvalues, for a matrix like what is given here, when you can take enough eigenvalues here, then you can break it apart, the vector itself, to be itself a sum of squares. We gave an example of this back in either 632, 689, or somewhere else in this world, where we talked about how you could rewrite any sort of symmetric form at all like a sum of squares, some of which were quite interesting. Things like if you have x of 1 squared plus 2x1, x2 plus x of 2 squared, then there's a way to write this as a sum of squares, where you may have to change the values of what it is that you're actually squaring. For example, this one just becomes x1 plus x2 quantity squared. So in this case, x of 1 tilde would be something like x of 1 plus x of 2. And the value that goes out beside the parentheses, this one right here, this is the eigenvalue of a particular matrix. If you diagonalize the matrix S that you get, then the diagonal matrix ends up being the eigenvalues of the original matrix you're plugging in here. And that's a fact that we're going to use, is that the eigenvalues of A get involved whenever you break something up into a sum of squares. That's going to be the main thing that we use from this theorem, that if you have something of this form in particular, then the eigenvalues of A can be used as scalars to write any vector going through this matrix as a sum of squares. We're also going to need this fact, and we'll mention this briefly, that if you take an orthogonal matrix, then the S times any norm 1 vector is also going to be of norm 1. And the way that we show this, and we'll see this actually used in the theorem, is that we're going to use the definition of the dot product of the inner product that we get. Recall, again, that if you take the inner product of two vectors, then that's going to be equal to y transpose times the vector x. So if I write this in that form, what I'm going to get is, this is sx, the vector, and on the left, I'm going to write s sub x transpose. Here, everything is real value, so I'm not taking any bars. But I can rewrite the transpose of two things as transpose of each individual thing as long as I shift around and switch the order of how I'm writing my vectors and or matrices. And if I rewrite this one, I can put parentheses around this and rewrite this as the inner product of S transpose X times X times the inner product of X. This is going back here. This is the same, using the same definition of the dot product here. Well, since S is orthogonal, its transpose is its inverse. S transpose equals S inverse. So I could rewrite this as S inverse X, comma, X for this inner product. And the inverse of any matrix times itself is just the vector X. And that's going to give me something of length 1 because I started with saying that the norm of the vector X was 1. That is, the square root of the norm of X, comma, X is equal to 1. So the inner product of X with X has to also equal 1. So now let's go through and talk about what we're doing. First, what we want to do is talk about this matrix and connect A to A transpose A. So the first thing we're going to use is this equality right here, which we've just proven a version of in the slide above, which is that the inner product of AX comma AX is itself a quadratic form. We know this because if you rewrite this, you have X transpose times a matrix A transpose A times the vector X. Since it's a quadratic form, the principal axis theorem is going to allow us to write anything in this inner product form as a sum of squares where the scalars are the eigenvalues of lambda 1 through lambda n. Since this is a quadratic form, this is equal to this, but the norm of AX with itself is also equal to the norm of A sub x squared. Now, you might recognize this because this is the norm of a vector that you would get in the range of A. Let's say, for example, that we come in with the assumption that the vector x has a norm of 1. Then finding the maximum possible value of this is going to give us the norm of A quantity squared. If we maximize the value of what this can be, the norm of A sub x squared, wherever the norm of x is equal to 1, then what we calculate from that is itself the norm of A squared. So that is exactly the attack that we're going to be taking. So here's how we're going to do it. We notice that, first things first, that the sum of these squares that I'm getting over here end up being 1 because of the fact that x tilde itself is of norm 1, and we're just using the definition of the norm there inside of R2. So the sum in the line above is a weighted average of the eigenvalues of lambda sub I by the values of x sub I tilde. To explain that sentence, this is something like, if I were to just take the average of what these eigenvalues were, I would just be summing up each of these eigenvalues and then dividing by 2. But a weighted average is possible here. As long as my scalar values, whatever they might be, add up to give me 1, then this would be a weighted average, where I'm counting lambda 1 to be a little bit heavier in my calculation than lambda 2. This is the picture that I have going on right here. This picture is a linear combination of the scalars, lambda 1 through lambda n, where these guys actually are the possible values, the real numbers that I could be getting out of this. Now, I'm choosing those to be the scalars and to focus on the lambda 1 through lambda n because I know something about these x sub I tilde squareds. I know that they sum to be equal to 1. That's exactly what I need in order to be able to define something as a weighted average. Now, let's think a little bit about this weighted average. The weighted average is equal to the norm of A sub x quantity squared. And so now I want to try and figure out, how can I make this as big as I possibly can? Well, how could I take a weighted average? Let's say, for example, I could choose what these x sub 1 and x sub n tilde are. And let's say that if I can choose that, I want to try and make this as big as I possibly can. Well, then probably something that I'm not doing is trying to just take an average of the eigenvalues that I get. Let's say my eigenvalues are 5 and 3. If I want to find the largest possible thing that this can be, given any choice of x sub 1 tilde squared to x sub n tilde squared, then what I want to do is probably not just take an average. I want to find the weighted average that gives me the highest possible value that I could get from here. And the largest possible value is 5. I could get as close to 5 as I would want to. And eventually what I can do is I could just say, oh, well, this is a weighted average as well. It's a really cheap weighted average. But the largest it could be is if I choose the eigenvalue that is the largest possible, and then make that scalar value equal to 1, and make the rest of them equal to 0. That's the largest that this value could possibly be. That tells us that the supremum of the norm of base of x squared is equal to this lambda max value that we've been defining from before. The supremum is in fact attained by a specific vector, so this isn't just a hypothetical. We can actually find a vector that makes this work. This is the vector that we could be plugging into this matrix that stretches as far as it possibly can when mapped through by the matrix A. So that's the idea behind this theorem, and a neat way to see how the principal axes theorem could be used in this respect. This sum of squares stuff ends up being useful because now we can think of these as weighted averages of eigenvalues based on whatever vector x that I might plug in here. As long as that norm of the vector x is 1, which just putting a 1 somewhere and zeros elsewhere gives us a vector of norm 1, then what we're calculating is involved with calculating the norm of A. So we're good to go. All right, so that gets us something pretty interesting here. We have found that that every vector, every matrix A has a norm to it, the square root of the absolute value of the lambda sub max value that we've been talking about from before. This is an example of a space of linear operators, by the way, which is the space of matrices. The space of n by n matrices is an example of a space of linear operators, but it's a special case. Whenever you're looking at the world of matrices, typically we're looking at things from the beginning when we're looking at finite dimensional vector spaces. Rn and Rm, Cn and Cm, whatever kind of field you're working in to the power of n, those are the canonical examples of finite dimensional vector spaces. In fact, up to vector space isomorphism, they are the only ones. The only finite dimensional vector spaces that you can have in this sort of, when we're looking at fields like R or C, are going to be of the form R to the n or C to the n. Some of you may know about finite fields, and those have separate vector spaces, and we aren't discussing those in this story. But when you start discussing the world of infinite dimensional linear operators, things start really blowing up. We have a lot to talk about in the world of infinite dimensional vector spaces when we start talking about linear operators that are defined on those infinite dimensional vector spaces. So just to clarify, finite dimensional vector spaces have operators. Finite dimensional vector spaces like Rn and Cn, I'll use like Rn as our example. So operators on finite dimensional vector spaces are in one-to-one correspondence with matrices. If, say, for example, you take this linear transformation L to be going from Rn to Rm, then you can find a matrix A, which is an m by n matrix, such that when you take a vector x and you map it through the linear transformation L, then that's the same as multiplying on the left by the matrix A. This is typically called the matrix representation theorem and is usually given in an undergraduate linear algebra course. What's the idea behind it? It says that if you have a transformation that satisfies two conditions, that is, that you can take scalars outside and you can break up two sums, just like we talked about with the inner product from before. If you have a function that satisfies those two properties, you can actually find that that linear transformation is just matrix multiplication. Linear transformation does the job. You can just say, okay, well, if I want to figure out what this linear transformation is, if I could describe it in a way that's something that makes sense to me, instead of just as a function, I can write it as just multiplying by a matrix instead. Let me give an example of this. Let's say that we have a linear transformation defined by the following. Let's say that the way that we define a linear transformation is that if we take a vector xy, which is going to be a vector xy inside of R2, and let's say I get another vector here inside of R3, and let's say I define it as something like this, x plus y, y, and then 0. Then this is an example of a linear transformation. One can go through and check and see that these two equalities are indeed true, that you can take out scalars. If you have alpha times x to the vector y, then you can also just take alpha times the vector that you get from calculating the linear transformation. You can also check to see that the addition of two vectors can be written in a similar sort of way. So the thing is this linear transformation could also be written as matrix multiplication. And one way that I could see that is I could start by mapping through the standard basis elements, L of 1, 0 and L of 0, 1, and see what I end up getting from that. If I map in through 1, 0, what I end up getting is 1, 0, 0. And if I map in 0, 1, what I end up getting is 1, 1, 0. You can check to see that if I take those two columns that I just got and combine them together into a matrix, that what I end up getting is exactly the linear transformation that I just discussed. That I could have, instead of just thinking of this as like a function mapping a vector from R2 to R3, I could have just said this is matrix multiplication by the matrix 1, 1, 0, 1, 0, 0. It's a way to rewrite functions in terms of matrices. And matrices, as we've seen a bit in our linear algebra courses, have a lot to say. When you write something down in terms of a matrix, you can diagonalize it, you can get an orthonormal basis for it. And once you've gotten some of those tools, you can start doing least square solutions to it. There's a lot that you could play with once you're into the world of matrices. There's a lot of connection, a lot of beauty in the interconnecting spaces there. So linear transformations and matrices in the world of finite dimensional vector spaces can be thought of as very much the same. There's a corollary from this theorem together with the theorem that we talked about in our optional segment just a little bit ago. And if you want to see the proof of this, go back and check out the optional segment. But a corollary of this is that all finite dimensional linear operators have a norm. In fact, they all live inside of a normed space. All of them live inside of some sort of normed space. Typically, the way we might write this is Rn cross M. Sometimes you also see it written as M, N cross M of some sort of field like R. These are the typical ways that you might write these, that you could define a norm on any one of these spaces. In particular, you get a finite value for what each of those things are, and it's something based off of the eigenvalues. But there are also linear operators on other things as well. Let me discuss a brief image of one that works on an infinite dimensional vector space. We have two examples of three, maybe more once we've recognized it. Lots of examples of infinite dimensional vector spaces that we get to play with. One example of an infinite dimensional vector space that we've been working with so far is the space of polynomials. And this could be with real coefficients if we want it to be a real vector space, or with complex coefficients if we want it to be a complex vector space. But the space of polynomials is an infinite dimensional vector space. Another one is the space of sequences, R infinity, the space of sequences with real coefficients. This is another example of an infinite dimensional vector space. There are particular subspaces of these that are also infinite dimensional that we've been playing around with, but these are two of the main ones. We've also talked a bit about the continuous functions going from A to B. This is another example of an infinite dimensional vector space. These are vector spaces in the sense that they satisfy all of the axioms of a vector space, plus there is no finite basis for any one of these three. So when I say infinite dimensional, I mean there is no finite basis for this. 1, x squared, x cubed, x to the fourth, so on and so forth, is an example of a set of linearly independent elements inside the space of polynomials that could go on forever. And you could just keep adding on more and more linearly independent things. So this finite set, any finite set of these functions that you have here, cannot be a basis because you could always add on another vector, another polynomial here. Same thing with R infinity, same thing with the continuous functions. These are all examples of infinite dimensional vector spaces. And we can define linear operators on these infinite dimensional vector spaces in specific ways. For any two V and W vector spaces over a field, then we define something to be a linear operator if it satisfies the same two conditions that we had before. Scalars can go outside of the vector, and you can break up sums with each of these. In the spirit of thinking of these like matrices, you will see us write this a lot. A times the vector u. Even though A is a function, we typically will not write parentheses around here. And the reason is, even if these are not matrices anymore, and to be clear, they're not, A times U can still be thought of as like matrix multiplication. So we're keeping that same sort of spirit when we write things like this. So what we have here is a definition of a linear operator on an infinite dimensional vector space, really any dimension of space. We know that in the space of any time that you're looking at finite dimensional vector spaces as your domain and codomain, that you have a linear operator that is really just a matrix. But if it's infinite dimensional, you're not necessarily looking at a matrix anymore. Let me give an example. Let's say that we have T going from the set of real sequences to the set of real sequences. And let's say what it does is that it takes a sequence, whatever it is, let's say it's S1, S2, S3, so on and so forth, and that it maps it to, you may remember this one now, the sequence that puts a 0 right on the very front and shifts everything over by 1. This is a linear operator between two infinite dimensional vector spaces. And there's not really a way to write a matrix that sends this sequence here to the other. Think, how would that matrix look? That matrix would have to take something like this and maybe try and turn these sequences into vectors, and then it would have to be infinite in its size. You'd have to keep making more and more columns and rows. Now, if you try and generalize it a little bit, which you're free to do if you'd like, although that's not our definition of it, you could think of the vector or the transformation T as like an infinite dimensional version of a matrix. If I wanted to, I could try and figure out where the ones and the zeros go in sending a vector like S1 to S1 over here, or taking elements of a basis like 1, 0, 0, and 0, 1, 0, so on and so forth, how these map over here, and then figure out where the ones and zeros need to go in an infinite dimensional matrix there. And in fact, there is some mathematical utility to that, but we don't call those matrices. Matrices are finite in their number of rows and their number of columns. So that would have to be named something else, and we call them linear operators. Many mathematicians still think of it like it would be a matrix, and that's why you see this little bit of a notation anomaly from what you might expect from having to map a vector through a function. So this is an example of a linear operator between infinite dimensional vector spaces. Now, linear operators are interesting because matrices have a neat property. Matrices are continuous. Here's what I mean by that. If you have that the vector x sub n converges to a vector x inside of, let's say that this sequence converges in Rn, then in fact, a times x sub n times a converges to ax in R sub n. That's what I mean by continuous, is that if you have something that converges in the domain of a matrix A going from Rn to Rm, then in fact, the corresponding y values, the corresponding range elements of going through that matrix, these also converge. A neat way to see that is this. A neat way to see that is we have that because we have xn approaching x inside of Rn, we have that their norm goes towards 0. But what could we say about the corresponding norm of ax times a sub xn? This norm right here is, we want to claim, also going to be very small. But only knowing this information, it seems difficult to know about what a does. So let's start here. Let's factor out an a out of both of these terms. And take a look at this like it is the norm of a times the quantity, this vector now, x minus x sub n. What we've done is we just factored out a out of both of the terms in the norm and the line above. Now we know that this is going towards 0, but I don't know what a is doing to this vector. Or do I? If this vector is pretty small, I actually have justification to say that a times that vector is also pretty small. What is it that gives me justification to do that? Remember in our corollary, we just said that every matrix has a norm. And what is a norm? It's the largest possible value that a times x minus x sub n can be, given what this value is. So for example, if x minus x to the n is of norm 1, then this is less than or equal to the norm of A. If this is of norm 1/2, then I could just factor the 1/2 outside. If it's of norm 1/3, I could keep doing that. Essentially, I could factor out the norm of x minus x of n out of this whole equation. This property right here is something called submultiplicativity. It's a long word, so I have to split it up to write it all. Submultiplicativity says that if I have the product of two things inside of a norm, then I can break it up with a less than or equal to as the product of the two individual norms. Let me walk through again why this should be true. Remember that this norm A right here is the supremum for all vectors x inside of Rn, where the norm of the vector x is equal to 1, of the possible value of the norm A sub x. Well, let's say that x minus x of n is something of norm 1. Well, then whatever this norm is, it can't be bigger than the norm of A. Can't be bigger than the norm of A because this is the largest possible that such a norm could get for A times a given vector. Here, that given vector that I'm thinking of is x minus x of n. And if it helps, you could write this like AY for a little bit. This A times Y is less than or equal to the supremum over all possible A times x's, where the norm of x is equal to 1. Now, that's me assuming that the norm of x minus x of n is equal to 1. But if it's equal to 1/2, it is going towards 0 after all, then I could say that I'm just taking that norm 1/2 and multiplying this vector times 2 and bringing the 1/2 outside. I can now think of this as 1/2 times something that is also still of norm 1. It was the norm of 1/2 vector that I had from before, just multiplied times 2 to make it of norm 1. That 1/2 that I have left over can just be brought outside. That's the 1/2, is that the norm of the vectors x minus x sub n can grow to be very small in that. That's a neat little connection that allows us to break up a product of two vectors, or make matrices and vectors inside of a norm here, and make it less than or equal to the norm like this. If you're a little bit still kind of on the fence about this, I recommend going back and seeing the full-fledged argument that we did back in video lecture 7-3. It was 7-3, right? I believe it was. It may have been 8-3. Nope, 8-3. That was it. Where we fledged out that the norm of A times B was less than or equal to the norm of A times the norm of B. This here, we're just replacing B with a static value, which is x minus x of n. Static, at least with respect to what the vector x could be. And we're getting that same sort of submultiplicativity in that argument. So now, if we know that this goes towards 0, well, this is a norm. It's a finite value, so this has to go towards 0. That means that this entire norm has to be going towards 0, which is exactly what we mean when we say A times x of n approaches A times x. So this satisfies our claim, which is that A is a continuous function whenever we're considering A to be going a linear transformation going from Rn to Rm. However, the continuity that we would get from finite dimension is not necessarily going to carry over into the world of infinite dimension, because there exist discontinuous linear transformations in the world of just infinite dimensional vectors. Now, I'm using a different term here than I have been using in the past. I believe I don't think I've defined functional. I don't think so. So let me go ahead and say that real quick, that the linear functional here is you could take a function f that goes from an infinite dimensional vector space and just lands you inside of the field you're working in, x to r. This is an example of like, take a vector and just give me a real number. An example of this might be something like f of a sequence, 1, 2, 3, 4, so on and so forth, just gives me the second value. And this is an example of what one of those functional vector spaces or one of those linear functionals might look like. It's something that goes from a vector space and just gives you a real number out of it. But there exist linear functionals that are discontinuous, that do not have a notion of continuity to them. And that's very different than matrices, because we have seen that whenever you have a matrix A that goes from Rn to Rm between finite dimensional vector spaces, that continuity is automatic. And the reason continuity was automatic is that you had a norm on that function that you were working on. Here, we're going to see that our linear functionals do not have to be continuous functions. Here's how we're going to show that. Imagine this, first of all, to be something like R infinity, where you're looking at the space of all continuous functions. So here's how we're going to do this. Let's first take a basis of that space, something like 1, 0, 0, 0, 1, 0, so on and so forth, all the way through. Then something that we know about linear functions is that once I know where a linear function takes every single basis element, I know where it's going to take every other element inside of that vector space. For example, if I know that where these 3 basis elements go, then I actually know where this vector goes, 1, 2, 3, 0, 0. And the way that I know that is, if I know where this guy goes, I know where this guy goes, I know where this guy goes, well, then I can write this guy as a linear combination of the first 3. This is 1 times the first basis element, plus 2 times the second basis element, plus 3 times the third basis element. And so because a linear transformation allows you to break up sums and bring scalars outside, then if I know what this linear transformation is going to do to this sequence, I know what the linear transformation is going to do to that. It's just going to take me to 1 times where the function sends the first basis element, plus 2 times where the function sends the second basis element, and 3 times where the function sends the third basis element. And you'll see me use this a good bit when we're talking about linear transformations. It says that if I know where the basis goes for a linear transformation, I know where everything else goes. So I define just saying where f of 1, 0, 0 and f of 0, 1, 0 and f of 0, 0, 1 go, then I can find everything else. I just have to break apart the sum and bring out the scalars. So let's see that here. First, I'm going to take an infinite sequence, which is a basis, and such that the norm of each element is 1. Seems like a good choice based off of the infinite dimensional sequences that I've been working on so far. Then here's how we're going to define our linear transformation. We're going to take f to be going from this infinite dimensional vector space to the real numbers by setting f of the nth dimensional, or the nth vector inside of this basis to be equal to n. F of x of n, the nth dimension, the nth vector inside of the basis for this space, to be equal to the index. In this example, what we would have is that f of 1, 0, 0 is going to be equal to 1. F of 0, 1, 0 is going to be equal to 2. F of 0, 0, 1 is equal to 3. You can definitely see that this function grows based on what basis element you're plugging into the function. Now, we can extend that linearly, and here is the exact formula that allows us to do that. This is us breaking up the sum and bringing out the scalars to see what value that we end up getting from this. Let's observe the following sequence. 1 over n times the vector x sub n. This is a sequence of scalar multiples of the basis elements, x sub 1 through x sub n, all the way to this, through this infinite countable sequence. So this sequence is a sequence of elements that if I try and observe the norms of each of these elements, 1 over n times the vector x sub n, I can bring the 1 over n outside, and I'm left with 1 over n times the norm of x sub n, which is just, since the norms of each of these elements were assumed to be 1, it's just going to be equal to 1 over n. Notice then that this in norm is going to converge toward 0, the 0 vector that is. That if I look at this as the sequence of 1 over n x sub n, this is converging to the vector 0 using the norm definition we've been looking at. And that's because 1 over n is definitely heading towards 0. So the sequence 1 over n x sub n has norm 1 over n and hence converges to 0 in norm. But take a look at where the y values go when I map them through this function f. Well, if I take 1 over n times x sub n, then what is this doing? A linear transformation can take the 1 over n outside, but I'm still multiplying, or I'm still mapping x sub n through this function to get the value n. This is 1 over n times n, which gives us 1 regardless of the value of n that we're using. So notice that we have a sequence of values, 1 over n x to the n, that's converging towards 0, but where the y values are going toward 1. That sounds to me a lot like a discontinuous function. The x values are not agreeing with what the y values are doing. The function f is not continuous at 0. One last thing I suppose I should mention here is that you might say, okay, well, John, isn't it the case then that just when you map in through the limit of the x values here, the f of the vector 0 is equal to 1? But that's not possible for a linear transformation. And the reason is, talked a little bit about this in the last video. If you try and multiply this vector 0 times 2, well, this is the same thing as the vector f of 0 just by looking at the inside. But I can also bring the 2 outside. So this is also equal to 2 times the vector f of 0. And subtracting f of 0 from both sides, we get that the value of f of 0 vector is equal to 0. So this is a contradiction. We've just seen that, at least, well, better to say, we've just shown that the function f cannot be continuous because these y values are approaching 1. They're not approaching 0. This is very difficult to start getting a picture of in your head because when we start getting to infinite dimensional stuff, we start just imagining the world of sequences, of polynomials. You can try, if you imagine, if you would like, an infinite dimensional world of a real vector space where you just have arrows and dimensions as far as you would like to go. But infinite dimensional, very hard to draw pictures of. So the way that I try and imagine these things as I go through and look at these propositions and look through at these proofs is I'm trying to get into my head what's really going on here. What is this function attempting to do? If I'm trying to draw a picture of this, I'm imagining you have a basis. This is the first basis element you have, x1, x2, x3, x4, x5, x6, x7, x8, and so on and so forth. Each of these is somehow in a different direction than all of the others. And what I'm doing is I am taking scalar multiples of each of those basis elements and getting them to go towards 0. But when I map those elements through to where the y values go, then all of the y values of the points in red are sticking around at 1. And because of this, they're not converging to where the red values are converging to in terms of their y values. They're not converging to 0. So that's the picture that we have for this type of proof. Well, because linear transformations involving infinite dimensional vector spaces are not necessarily continuous, we have to be a bit careful. Continuous is absolutely what we want. Let's be clear. Continuous gives us so much to work with. We've talked about continuity all the time in the weeks previous to this. In fact, continuous functions seem to give us exactly what we're looking for in many of the cases. Continuous functions, when they converge uniformly, the limit that you get is continuous. You want all of these things to still be true when you're working in a space like the linear operators on a vector space. So that's what we're going to be analyzing a little bit. We'll take some time with this one. And that's essentially what we'll be doing in this last part of 9-2 is trying to talk about this notion of continuity in these sorts of spaces. But there seems to be a connection between what we were doing in the world of finite dimensional vector spaces and what we're doing here. Because finite dimensional vector spaces, we saw that matrices, for example, were continuous functions when considered as functions from one vector space to another, but they also had a norm. And in fact, it turns out that those two things are exactly related in the world of linear operators. That is, if you have something that is continuous, then it also has a norm. And the way that we describe that here is using a term called bounded. Now, let me describe bounded here as it's a little bit different in the notion of bounded that we typically use to describe functions. When we describe functions, typically we mean bounded to mean something like, say, a sine or a cosine type function, where the highest and the lowest possible points on that function are finite values. We will say a linear operator going from one vector space to another is bounded if we can say that the norm of the y values of that is bounded by a scalar times the norm of the x values. This should look a little similar to Lipschitz continuity. It really should. This should feel a little bit like Lipschitz. Is that you have a linear operator going from one vector space to another being bounded whenever there is some sort of constant that bounds the norms of y values by the norms of x values times that constant. Recall that definition of Lipschitz, by the way, which is saying that you can take the difference between the values of f of y minus f of x and bound that above by some m times the difference between y and x. Here we are replacing the distances with norms because we're in a normed vector space, and we're using v as our particular vector of choice here. This is going to give us the norm of a bounded operator. Whenever we have a bounded operator, the best choice of value for this m ends up being the norm of that operator. That is, we are going to define the norm of an operator to be exactly the operator norm, the one that we defined back in the previous week's video lecture. This is why we talked about it back then, so that we could have some familiarity with it and start working with it a little bit. This is the operator norm of the matrix A. Note by definition, and this is something we used up before, that the norm of A times B is less than or equal to the norm of A times the norm of the vector B from these two spaces. So this sort of operator, this sort of norm, this sort of boundedness for this space ends up being connected directly to the continuity of these things. For linear operators A, V, to W between norm spaces, the following are equivalent. If something is bounded, then it's in fact uniformly continuous. It's continuous in the strongest sense. In fact, you could go farther in the uniformly continuous. You can say Lipschitz continuous. You can say that with the strongest sense of continuity that we have, that the matrix, that the operator that you're working with is uniformly continuous. This is also equivalent to this. This one might seem a little strange. The fact that A is continuous at a specific vector at 0. Here's what that is saying. These three statements are meant to be equivalent. A is bounded, A is uniformly continuous. Pretty nice, because these are very separate conditions. However, 2 definitely implies 3. 2 is that A is uniformly continuous, hence it's just normal continuous at a specific point of 0. That's absolutely true. But what's neat is that these two statements are equivalent. You could go backwards. If your operator is linear and you know your function is just normal continuous at a single vector at x equals 0, then in fact, you know it's not just continuous at 0, it's continuous everywhere. You know that's not only continuous, it's uniformly continuous. In fact, you know it's Lipschitz continuous. You have the strongest sense of continuity that you might want to muster for this operator. And it just comes from having normal continuity at a specific point. A neat thing about this is that this is what we say when it comes to continuity here. And in our homework for the previous video lecture, we saw an example of a very weird discontinuous function. Essentially, if we aren't in the world of bounded operators, if we aren't in the world of these uniformly continuous operators, the types of operators that we're looking at are a lot like what we had in the reading for homework last time. We're also looking at operators that look a lot like what we had here in this example, this counterexample, to say that there exists a discontinuous linear functional. Things that are very strange and very weird. These are very, very complex, not nice to work with functions, many of which are indeed dense in the graph when you consider what they look like, especially these that are linear functionals. They are indeed bona fide dense in the graph of the functions that you would get from this. They are very, very strange functions. What we want to be looking at are the world of linear operators that are bounded, uniformly continuous, and or continuous at 0. Just that is enough, because without even having continuity at a single point, we're looking at functions that are crazy, crazy to look at. So this is the world that we discuss when we discuss the world of linear operators more often than not. So this is our generalization of matrices. Matrices in terms of infinite dimensional linear operators are these bounded, specifically bounded, linear operators between two vector spaces. Let's talk a little bit about this proof about why these three conditions are all the same. We already have that 2 implies 3. We're good on that front, because if something is uniformly continuous, it is normal continuous at a specific point. What about 1 implies 2? If the norm of the matrix or the norm of the operator that we're looking at is 0, then you have to be looking at the 0 operator, so you're done. Otherwise, you let epsilon be greater than 0, and we're going to show uniform continuity. The way we show that is we start by taking 2 vectors inside of our domain space that are within delta of each other, and eventually hope to show that in y values that they are within epsilon of each other. So we'll start by fixing epsilon to be greater than 0, and we're going to choose delta to be equal to epsilon divided by this norm of the operator A that we're defining. And we're going to use that inequality that we were talking about from before, the one that allows us to submultiplicatively take apart two norms of A and V minus W. Once we take that apart, we have the whole thing, because this gets replaced with delta, or something less than delta, which is equal to epsilon over the norm of A. So the norms of A cancel, and I'm left with epsilon. For 3 implies 1, we're going to do the contrapositive. And in fact, we've already done the contrapositive. If A is not bounded, then there exists a sequence of these x sub I that have norms equal to 1, and such that the norms of A times x sub I could be equal to n. In fact, you can just find, with respect to these vectors of norm 1, you can continue to find larger and larger vectors, A times x sub I, that get to be as large as you would like them to be. And then what we do is we do the same thing that we did in that example, which is we just start taking a look at the sequence of the 1 over n times the vector x sub I. And that's going to be something that is in norm, and the x values converges to 0, but when you map them through the linear operator, their values are always going to be equal to 1. What's allowing us to do that is the fact that A is not bounded, which means that regardless of what bound that we might put here for M, there's always an A times V that makes it bigger. And for that A times V that we get, this can always be of norm 1. We can always scale it down if we want it to be. So you can make this bigger than n, or n plus 1, or n plus 2, or n plus 3. You can always find a norm for the vector A times V that gets it to be as big as you'd want it to be. And that's the whole proof. That shows that these three things are equivalent. And it's crazy because this is one of the strongest proofs out there. It says that continuity, normal continuity at a specific point, gives us the strongest form of continuity everywhere for the function. This is one of the strongest proofs out there, and it's remarkable how short it is, how little we have to talk about, because all of these three conditions are so closely knit together once we add in the condition of linearity. Now, notice that this is only true for linear operators. I can't say anything about functions, even as simple as like f of x equals x squared, after looking at this theorem, because f of x equals x squared is not linear. The types of operators that I'm looking at are things that work neatly with scalars and sums that get brought out in that particular way. And in order to do that, we have to say that our type of function is very rigid, it's very strict. In R3, the types of linear operators that we typically see are things like planes. Things like that would be something like going from R3 to R2. Or you could see lines. You can also see hyperplanes if you're familiar, something that's like a version of a two-dimensional plane, but it's actually three-dimensional. You could see some examples of these things. However, a matrix maps through. That's what the sort of thing is that you're looking at. These are not going to be things that have any sort of curvature when you try and draw them. There's no picture of anything where you have a parabola. These are completely linear. The picture that I have in my mind when I think of linear operators are planes. You're mapping something from R3 to R2 in there. The mapping that you're doing is you're saying, take a point in R3 and I'm going to map it through in this space. So here you have your first domain space, and then you have your codomain, which could be multiple dimensional, and when it spans out is going to be a plane. Just a couple of things to kind of wrap us up here before we get into our final example. One thing is that this space itself is worth discovering. And we'll talk a little bit briefly about it in the next week's video lecture, that L of V comma W is defined to be the set of all bounded linear maps, A going from V to W. This is an example of a normed vector space. In fact, whenever your range space is complete, LV comma W is a complete space. And it has all of the nice things about complete spaces that we want. I'm not going to go through that proof because if you look through it a little bit in the textbook, you'll notice that it's very similar to something we've already done in video lecture 7-1. You might notice from the theorem that the flavor of this theorem looks very much like the one that we used to show that that set about bounded functions from x to y is complete. And the proof is indeed very similar. So if you want to see some of those details, check out the text. I'll, of course, be looking around in perusal for some of the things you might be asking about. I thought I'd change that typo for respectively. Crazy that didn't go through. There you go. So let's go through an example for showing that something is a linear operator. And then let's ask if it ends up being continuous. Here is the function capital F going from the space of continuous functions that are defined on the closed interval from 0 to 1. And let's take all of those continuous functions and send them to a real number. And here's how we're going to do it. U is itself a continuous function from 0 to 1. It's defined at any value that I might plug in going from 0 to 1. So I'm just going to plug in 0 for that function. U of 0 is a value in the real numbers. It's the value that I would get from plugging in 0 into the continuous function that I'm calling lowercase u. Let's show that f is a linear operator going from one space to this other one. Then we'll ask if f is continuous. To show f is a linear operator, I need to show two things. The first thing is I need to be able to say that if you take alpha u plus beta v as two functions inside of the continuous functions from 0 to 1, then that's actually equal to alpha of fu plus beta times fv. So let's see if we can do that. F of alpha u plus beta v is taking whatever this function is that we might get, alpha u plus beta v, and plugging in 0. But how do you add two functions together? You just split them apart and then evaluate them at each of the individual functions. Same thing when I have like an alpha multiplied times a function. That's just going to be multiplying each of the y values of the function times alpha. So this works exactly like we would like it to be, and in fact is exactly equal to what we have over here on the right-hand side. Just plugging in what we know f of u and f of v to be defined to be, which is u of 0 and v of 0 respectively, that gets us the exact same thing on both sides. So we're good to go. So yes, this is a linear operator, and we can show it just using this one step. So we're good to go. Now the question is f continuous? We can show this one of two ways. So we can show one of two ways. One, we can show if u sub n converges to u in the space of continuous functions from 0 to 1, then that implies that the values f of u sub n, which is equal to u sub n of 0, converges to u of 0, which would be equal to f of u in this space. If we actually take a look at this, then convergence inside of the space of continuous functions is actually uniform convergence by what we were doing back in week 7. So we automatically can find that we get this pointwise convergence for free. So this is actually very easy to show in that one direction. But now, because of what we've been talking about, we have a second way to show it in case that's maybe not the nicest thing to do, which is that we can show f is bounded. And again, what that means is that we want to show that the norm of the value that we get out of f of u, which is really just an absolute value because this is a real number that we're talking about, it's u of 0, that this is less than or equal to m times the norm of the function u inside of the space of continuous functions for some m. And we can get this. This is also possible. First, let's recall what this norm of u is going to be. This is what we also have been calling the infinity norm. This is, recall, that the norm of u, c(0,1) is equal to the maximum value as x goes from 0 to 1 of the absolute value of u of x. So it's the maximum value of what this absolute value of u of x is. So note that, oops, doesn't want to do anything. There we go. So note that f of u, which is just the absolute value of u of 0, is absolutely going to be less than or equal to just this value. And this is by definition of maximum. If you want to evaluate the function u at 0, well, then whatever it's going to be, it's less than or equal to the maximum possible value that the function u can take on the interval from 0 to 1. So m equals 1 is a fine bound, and f is bounded. Because this right over here is exactly the bound of u, or the definition of the norm of the function u on the space of c(0,1) that we were talking about from last week. So m equals 1 is just a fine bound, and we can say that that's good to go. In fact, if we wanted to actually find the bound, we could. So we can check that actually the norm of this functional f that I have given here, that this norm is equal to 1. You can check that by trying to find a function that does satiate this. And the hint for that is just to take the function where u of x is equal to 1 for all x inside of 0 to 1. Just the constant function 1 will give you something that evaluates to be 1 at 0 as well as everywhere else. And that will give you an equality on this space. So that gives us this notion of continuity here. Okay, pretty neat stuff. So we've shown a little bit of neat things about this notion of continuity and gone through an example of what something here might look like for linear operators. And we're going to have plenty more examples. What I'm trying to focus on in these last couple of weeks is to give a lot more examples of what these transformations, operators, what have you, all might look like so that you can get a little bit more intuition with these as we come and start ramping into our final here. So hopefully these examples have been helpful and that you've enjoyed these video lectures. As always, it'll be good to see you around in the discussion boards. Thank you so much. Have a wonderful day.